Hello, welcome to the channel. We are continuing our integration by parts sequence and we are in the last steps of it, so problems get trickier, and today we have an integral of arcsec of x from 1 to 2. It's a definite integral. For those of you who are new here, there is a playlist which contains all of the videos of this topic. I'll put the link to that playlist in the description. Alright, now let's see what we can do with this integral. Well, first step is to notice that this integral can be written as arcsec of x times 1 times dx. And then we can use integration by parts. Well, we had a similar integral in the previous video, except there was an x here, and we used x dx instead of noticing 1, as we do right now. Okay, naturally, we'll take u as arcsec of x, and dv as 1 times dx, well, just dx. Okay, now what is du? I'll put a question here, and first let's write v, it's just an x. In the last video I've used u as arcsec as well, and I wrote that du is, last exercise, I wrote du directly as 1 over absolute value of x times square root of x squared minus 1 dx. And I've mentioned that it's kind of a table value that some of you should know. But this is the thing that does not appear a lot, so you are better know how to derive it. And I said the clue for you will be that you can express arcsec of x, secant of x, as arccosine of 1 over x. Well, considering that domain of this function is absolute value of x bigger than or equal to 1. Alright, in the last exercise I used the fact that derivative of arcsec of x is this and gave you the clue. But now I have a nice opportunity to demonstrate the derivation of arcsec, and I think I'll take advantage of this. Right, now without losing some time we can go ahead, and I'll make a remark here, of course. So we have a derivative of arcsec of x, and as I said earlier, we can express this as the derivative of arccosine of 1 over x, and this is the whole idea. Well, here of course we know that the domain of both functions, like arccosine of 1 over x and arcsec of x, is x, absolute value of x is bigger than or equal to 1. Well, first let me write that derivative of arccosine of function, maybe some of you just forgot it, it's, let's say, arccosine of y, it's minus 1 over 1 minus square root of, like square root of 1 minus x squared. Just to remind you that the derivative of arcsine of x is the same thing but with a plus sign. Okay, now keep in mind this little remark. We can go back to our initial problem, which is arccosine of 1 over x, so you can see that it's 1 over square root of 1 minus 1 square root of 1 minus 1 over x squared times, like it's a composite function, namely we have 1 over x inside, so we need to multiply by the derivative of what's inside, namely 1 over x. It's a chain rule, and the derivative of 1 over x is what? It's 1 over x squared with a minus. Right, so let's write it here. So we multiply this by minus 1 over x squared, and then just cancelling out these minuses here and making some algebraic operations, we can obtain 1 over x squared times x, well, I wrote it directly, I hope we won't have any problems in this switch. It's just 1 minus 1 over x squared, and then it turns into this one. Okay, then we can write it as follows. It's 1 over x squared times x squared over x squared minus 1, right? There shouldn't be any problems in this transition as well. Nevertheless, if you have some questions, please write in the comment section below. Now, in the end, we have 1 over x squared times, well, we can express this as follows, and square root of x squared minus 1. Now, this over here can be written as absolute value of x is from the definition. Like square root of x squared is absolute value of x. Never forget this absolute value here. Now finally we can write this as 1 over, well, since x squared is also by definition the product of two absolute values of x, we can here cancel out one of them. It's here, like imagine this. We are cancelling out 1 and 1 remains. So we have in the end absolute value of x times square root of x squared minus 1, as we wanted, as I mentioned it here. So we have our value for derivative of arcsecond of x, and in the previous problem we had an indefinite integral. So I've written an answer in a general form for different values of x. But in this particular problem, I'll write it here. In our problem, since x is between 1 and 2, it's a definite integral, then it means x is bigger than 0. So absolute value turns into just x, like this, equals in the end to 1 over x times x squared minus 1. It'd be better to write it here and mentioning that x is bigger than 0. Okay, it's our remark. Not that short it is, but now I feel some completeness, because not too long from the previous video there is a derivation of the derivative of arcsecond of x. Good. Now we can proceed with our problem, which was to finding a definite integral of arcsecond of x. Now that we have finally obtained our question mark here, we can write that we want the form of u times v minus, well, integral of v times du, and it will then be what? U times v will be x times arcsecond of x, x times arcsecond of x from 1 to 2, it's a definite integral, don't forget, minus an integral, again definite one, from 1 to 2 of, now we have v, which is just x, and we multiply this by du. Let me write it here as well, that it's du will be this, particularly for our integral with boundaries from 1 to 2. So it means, okay, I'll write it without any reductions. It's dx over x times square root of square minus 1. Here I didn't put differential because we were just finding a derivative of arcsecond, but if you are taking the variable u here, then finding du, we need to write differential as well. In multiple choice exams, or also for engineers, I think it might not be that much of a deal, but in a written exam it may cost you some points. Alright, now I don't want to repeat what I've written just now, and instead just cancel these out here and write that it's an integral of dx over square root of x squared minus 1. Alright, here comes the second part of this video, this exercise, which is computing this integral. And if you remember, in the last video we had a similar integral, except there wasn't any boundaries, and we had x dx here. It allowed us to use substitution method, or just see that just the derivative of what's inside the denominator can help us here with differentials, basically the substitution method. But here we don't have such treasure, and for this we'll use the inverse second substitution. I hope I'll make a video explaining the whole idea of this substitution and where should we use it. But for now I'll just explain the substitution for this particular case. In fact, I did the same in exercise 9. And there I think I've explained pretty much the theory of the inverse substitution of arcsine of x. But for the second of x, I think I'll make another video, because it may take some longer time. Alright, first let's evaluate what we have here. Here we can write this again as x times arc cosine of 1 over x from 1 to 2 to make the life easier for us at this very place. And as for our integral, for this step I'll just duplicate it to write our answer of our cosine of 1 over x using Newton-Leibniz rule. First we put 2 times our cosine of 1 over 2. It's pi over 3, right? The cosine of pi over 3 is 1 over 2. Minus 1 times our cosine of 1. Our cosine of 1 is 0, since cosine gets the value 1 at 0. So it's 0 here. We can just skip even this part and write directly minus. So as for our integral, as I said, I'll use, for this we'll again make the remark here. The short rule is that whenever you see the structure of square root of x squared minus 1, you should use an inverse second substitution and see if it works. So in our case we can write x is equal to secant of, say, theta. Then dx will be what? It's secant of theta tangent of theta d theta, right? It's derivative of secant of theta. Now the main part comes is that, like in this case, x squared minus 1, it just turns into secant square of theta minus 1, and secant square of theta minus 1 is just tangent square of theta. Little note, like it's just cosine square minus 1, which is sine square minus over cosine square, right? Because sine square is just 1 minus cosine square. Alright, and after this point we have tangent of theta. And that's an important point of this substitution, to define the sign of tangent of theta, because we cannot just write tangent of theta here. It has an absolute value in it. I'll dive perhaps into the details of this in the video that I'll make, but for now just a little note that the graph of arc cosine of 1 over x, or just arcsecant of x, has the following form. And here roughly it's like this, with an asymptote of pi over 2. Here it's 1, it's pi. Now this is the graph of arc secant of x. Here we have x. Okay, now I'll analyze only this part, because in our problem, again, I'll write it where to write it so that it suits best. I think we can make remark here as well, like here. In our case, x is bigger than or equal to 1, so we only have the right part of this. So it means arcsecant of x is less than pi over 2. Now, arcsecant being less than pi over 2 means that theta is less than pi over 2, right? On the other hand, we know that, well, naturally it's like arcsecant of x is bigger than or equal to 0 in this case. Like, it's defined as such. And then theta is bigger than or equal to 0. So theta being between 0 and pi over 2 implies that tangent of theta is bigger than or equal to 0. And it's our main point here. Well, let's close this as a remark. Let's write it creatively. Let's put this direction here, and then we have that this is equal to tangent of theta. Well, I hope it's clear. Again, I repeat, if you have some questions, write in the comment section below. The main thing that we obtained is that tangent of theta in our case, like from 1 to 2, it will be greater than or equal to 0, which means that we can write that absolute value of tangent of theta is just tangent of theta. Now our integral, remember we had this integral. Oh, I forgot about boundaries. Let's write them quickly here. Boundaries. If x is 1, then what does it mean? It means that 1 is equal to secant of theta, equal to 1 over cosine of theta. Then cosine of theta is 1. Which angle is this? It's 0, right? Cosine of 0 is 1. So theta is 0. And x is equal to 2. In this case, we have that theta is equal to, let's see, 2 is equal to secant of theta, and it's 1 over cosine of theta, namely cosine of theta is 1 over 2, and it's pi over 3, right? Right. Just checking if it is pi over 6, because it must be either pi over 2 or pi over 3. So we have like theta is equal to pi over 3 here. It's also good. So now we have, I think, everything to resolve the issue with this integral that took too much of a time. But I think it was a nice exercise to refresh your minds and learn to think critically. Okay, now dx is secant theta tangent theta d theta, right? It's from here. And we've just shown that x squared minus 1 with a square root will be just tangent of theta, right? So it's tangent of theta. Now the whole expression is equal to, well, don't scare yourself with all these things. It's the thing that you need to understand, and in fact after some point you can just directly write that it's equal to tangent of theta. It's just that I'm showing you for the first time and it took so long. And here we have 2 pi over 3 minus an integral of like from 0 to pi over 3. Here tangents, they cancel out each other, and we are left with the integral of secant theta d theta. Yeah, After this, we can again write 2 pi over 3 minus an integral of secant theta d theta. I think we've covered this in one of the exercises. Nevertheless, it is ln of secant of theta plus tangent of theta, and additionally we have boundaries here from 0 to pi over 3. Okay, all that remains is to compute these limits or boundaries and write a final answer. Now, ln of, first we put pi over 3, secant of pi over 3 plus tangent of pi over 3 minus with a minus, so it's a plus. Imagine here we have some brackets. So it's ln of secant of 0 plus tangent of 0. Now this in the end is equal to 2 pi over 3 minus, well, secant of pi over 3, what's that? It's 1 over cosine of pi over 3, which is 1 over 2, so basically it's 2. As for tangent of pi over 3, it's, I struggle to remember, so let's just write that it's sine of pi over 3 over cosine of pi over 3, and see what we have here. Well, here we just computed it's 1 over 2, and then sine of pi over 3 is square root of 3 over 2. So it's what? It's just square root of 3. Yeah. So we have 2 plus square root of 3. Keeping that in mind, it's ln of, well, we can write without absolute value because it's positive, plus square root of 3. Okay, now plus ln of, well, secant of 0 is 1 over cosine of 0. It's 1, and tangent of 0 is sine of 0 over cosine of 0. It's 0. So we have ln of 1 here, ln of 1, and this itself is equal to 0 from definition. E to the power of 0 is 1. So we have this pretty answer in the end. Okay, here we are. It was rather a long exercise, I think, because I dive into the details of inverse second substitution, also the, well, here it was inverse second substitution, also the derivative of arcsec, as I promised in the last video. I hope you enjoyed it. Here is what we did. If you have any questions, write them in the comment section below, and see you on the next videos. Bye.